Today we're looking at all 5 learning targets from Unit 2. Within this video I've embedded one question directly from the test, so take detailed notes and you'll be sure to get that one question correct. So as we get started, one thing to keep in mind, and this works for learning targets 2A, B, C, and D, when it comes to graphing inequalities on a number line, if you have greater than or equal to or less than or equal to, you're going to use a closed circle at the point. That indicates that that point is a possible solution. Whereas if you have greater than or less than, you would want to use an open circle because that point is not a possible solution. Also, in terms of shading, if you have greater than or equal to or greater than, you're going to shade to the right. And if you have less than or equal to or less than, you'll shade to the left. Now that's assuming that the variable is on the left side of the inequality. But keep in mind you can always reverse the inequality so that the variable is on the left side. So for instance, if you go through solving and you end up with 5 is less than x, you could always reverse it so that x is greater than 5. So let's go ahead and start looking at some examples. As we're going through this, I'll give you an example problem. Just pause your video until you've had a chance to solve it, and then we'll talk through the solution. So here's your first one. X is greater than or equal to 5. So when you graph this, you're going to have a closed circle at 5 because it can include that point. And we shade everything to the right because those are possible solutions for this inequality. The next one, we have x is less than negative 7. So for this, we've got an open circle at negative 7 because it cannot include that point, and we're shading everything to the left. So for 2a, it's simply just being able to graph these inequalities. No solving involved, just graphing. Once you get into 2b, c, and d, you're going to have to do some solving. So please keep in mind the flip rule as you're going through this. And what the flip rule states is that if you ever multiply or divide by a negative number, you have to flip the sign. Now that's only true for multiplying or dividing negative numbers. So let's look at our first example. Again, pause your video till you've had a chance to solve and graph. So here, as we go through and solve, we end up that r is greater than 4. So we're going to have an open circle at 4, and we're shading all the numbers to the right on the number line. Here's your next example. Again, pause your video till you've had a chance to solve and graph. So first step here is we're going to have to distribute that 4. Go through and solve, we end up that x is less than or equal to 3. So we'd have a closed circle at 3, and we're shading all the numbers less than 3. Here's an example of something we've worked on a couple of times in warm-ups. So we've got 4 inequalities and 5 possible solutions. We want you to go through and solve and then check all the possible answers for those inequalities. So for the first inequality, we end up that x is less than or equal to 8. So all the red x's represent all the less than or equal to 8's. Next one, we end up with x is greater than 4. Now since it doesn't have the equal to piece, we can't check 4, but we can check everything that's greater than 4. Third inequality, we end up that x is greater than 12. None of the possibilities are greater than 12, so we don't check any boxes there. And then the last one, we have x is less than or equal to negative 3, so negative 4 and negative 8 should be checked there. So for 2c, we're now looking at when variables are on both sides of the inequality. One thing to keep in mind, as I'm going through these solutions, the first step that I always do is get my variables together. Now, there are multiple ways that you could go through and solve these, so there isn't a definitive first step, but since I like getting my variables together, that's the way that I'm going to show it to you. And I think for those of you that are struggling with this concept, if you take similar first steps, it will help make these inequalities look more like the ones that we saw in 2b. So for this, first thing I'm doing is I'm bringing my 4x over by subtracting. So as I go through and solve, I end up that x is less than 3. Notice I had to apply the flip rule there. So we have an open circle at 3, and we're shading everything to the left. Here's another example for 2c. So in this case, first thing we need to do is distribute. Then we can go through and solve. So we end up that x is less than or equal to negative 7. So we have a closed circle at negative 7, and we're shading everything to the left. Now here, Mr. Dunn and Mr. Braychek have gone through and solved an inequality with variables on both sides. Please identify who did it correctly and who did it wrong, and also tell what that person that did it wrong made the mistake at. So in this case, Mr. Dunn was correct in his solution. Mr. Braychek, when he was combining his variables onto one side or the other, he forgot to use the inverse operation. So make sure when you are solving problems like this that you tell what the mistake is that the other person made. So for 2D, we're now looking at compound inequalities. These were this was the learning target where we were writing on the desks and creating the graphs. So anytime you see a compound inequality where we've got this in the middle, you know that that's going to be an AND situation. You have to break it into two inequalities. So we've got 5 is less than or equal to 2x minus 5, and 2x minus 5 is less than 7. As you go through and solve, on the left here we get x is greater than or equal to 5. That's indicated by this blue graph. On the right, we get x is less than 6. That's indicated by the red graph. This purple graph is your final solution. So it includes 5, goes up to 6, but does not include 6 because it's not equal to 6, and the points in between. Please make sure when you are solving this on the test that you only show this final graph. I've used the red and the blue to help you in your understanding of where that intersection is. But on your test, please make sure that you only show that final graph. So here's an OR compound inequality. So just like we did in class, you're going to go through and solve each inequality. We got x is less than 0, so an open circle at 0, shade to the left. Or x is greater than or equal to 3, so closed circle at 3, shade to the right. Now this is what your final graph would look like. Now keep in mind with ORs, if there were an overlap between these two graphs, you'd be looking at all real numbers. So I know there was some confusion in class as to when do we do the overlap, when do we not. With ORs, you're covering anything that is covered by either graph. So in this case, we keep exactly as this because there is no overlap. So the next step I want you to do, here is a compound inequality graph. See if you can write out the compound inequality. So in this case, we have x is less than or equal to negative 2. We know that because there's a closed circle at negative 2, and it's shading to the left. Or x is greater than 4, so an open circle at 4 and shade to the right. We know that's an OR because they're going in opposite directions. Here's another one. See if you can write the compound inequality for this. So here we have negative 4 is less than x, which is less than or equal to 11. We know it's less than here because it's an open circle. We know it's less than or equal to here because it's a closed circle. And then we simply take where those dots are located on the number line. Now this might look familiar to you back from Unit 1 when we were dealing with domain and range. We wrote these in very similar fashion. So keep in mind that when you're writing a compound and inequality, you have your x in the middle, your number that was on the left here, and make sure you pay attention to whether you have an open circle, closed circle, and then your number that's on the right. So now let's look at Learning Target 2E, which was solving and graphing linear inequalities. For this, you're going to have to keep in mind the idea of a dashed line and a solid line. You'll use a dashed line when you graph if it's less than or greater than, and you'll use a solid line when you graph whenever it's less than or equal to or greater than or equal to. Now these are very similar concepts to the idea of an open circle, closed circle. A dashed line means that the numbers on that graph are not possible solutions. And a solid line means that the numbers on the graph are possible solutions. So very similar to the open circle, closed circle concept. So now go ahead and graph this linear inequality. Keep in mind the idea of open circle, closed circle, and then also shading. So here we know it's going to be a solid line because we have the equal to piece. Our y-intercept is at 4. Our slope is down 1 over 2. And we shade below because we're dealing with that less than or equal to piece. So we're shading below that line. So anything in this shaded region and the line are possible solutions. So if we take an ordered pair anywhere in there, such as 0, 0, since that's in the shaded region, and plug it in for x and y, this inequality would be true. Here's another example. Go ahead and graph and shade. So here we have a y-intercept of -4. Our slope is a +3. It's a dashed line because we don't have the equal to piece. And we're going to shade above because we're talking about the areas that are greater than. So again, anything in this shaded region, not including the line because it's dashed, would be an example of a possible solution to this inequality. Let's look at when the linear inequality is written in standard form. So here, the way that we do this, remember, is to find our intercepts. So 12 divided by 2 is 6, so we know it's going to cross that x-axis at 6. 12 divided by -3 is -4, so we know it's going to cross the y-axis at -4. It's a solid line because it has the equal to piece, and we're shading above because we're talking about the greater than. So again, anything in this shaded region, including the graph, or the line, pardon me, because it is a solid line, are possible solutions for this inequality. Here's another example in standard form, so go ahead and try to graph that. So here again, we know our intercepts. 40 divided by 8 is 5, so we know our x-intercept is going to be 5. And 40 divided by -5 is -8. It's a dashed line because we don't have the equal to piece there. And we're shading below because it's less than. So anything in the shaded region, not including the line, is a possible solution. Here's a list of all the videos that we had for Unit 2. Keep in mind that if you have notes for 2A, B, C, D, and E tomorrow during the test, you will get that bonus half point.